Jnanam Paramam Dheyam. Knowledge is supreme.
Alright, so we are nearing the end of our discussion of electronic spectroscopy. This really is the climax of our entire discussion of electronic spectroscopy. What we will try to do now is, using the principles that we have learned of quantum chemistry, quantum mechanics and symmetry, we are going to do a case study for once. We will try to see what the spectrum of benzene looks like and why it looks like what it does. We will try to assign the bands of benzene to the best of our abilities, and while we do that, we will learn something else that is called vibronic coupling, right. So, we start with the electronic states and transitions of benzene. All the figures that you see except the ones that I have drawn are from Harrison Bertolucci's book. This discussion has been done very nicely in Harrison Bertolucci's book. You can follow it for this part, right. If you remember, the last time we met, which seems like a long time ago, we had discussed the case of oxygen, and in oxygen we had said that the electron configuration was 1 pi u4, 1 pi g2, alright. So, what is a unique feature of this? The highest occupied molecular orbital that we have is doubly degenerate, and these orbitals have 2 electrons. So, in the simplest case scenario, we just draw 2 orbitals and 2 arrows pointing in the same direction, right. But as we learned, if we do a little more treatment, little more detailed treatment of this scenario, what we do is, in order to find the symmetry of the state, we need to take the direct product of the symmetries of the orbitals that are singly occupied, and in this case those orbitals are pi g. So, what we did was, we did pi g cross pi g, and in doing that we obtained 3 different states, 3 different symmetries: sigma g plus, sigma g minus and delta g, alright. And the other thing that we discussed is that you cannot just assign singlet and triplet to anything and everything here, because if you take singlet and triplet of all these, you get a total of 16 states, but then not all of these states are allowed by Pauli principle. So, in order to maintain a total wave function that is antisymmetric, we found that we end up only with 6 states, and the 6 states makes sense, because if you remember, we had drawn those boxes, 4 boxes, and we tried to fill with 2 electrons. There also we had obtained 6 states. So, the 6 states we obtained are singlet sigma g plus, singlet delta g and triplet delta g minus, and we had discussed that the triplet state is the lowest energy state and the other 2 are higher energy states. We had discussed what the energies are, and we had discussed how, first of all these 3 states arise out of the same electron configuration, right. It is just a combination of different spatial and temporal parts corresponding to the same electron configuration, which is this 1 pi u4, 1 pi g2. That is the first thing to understand, that the same electron configuration can actually give you different states. And secondly, we had said that of course, this transition between them would be not allowed, there will be spin forbidden, but still there can be a little bit of transition, because you can have spin orbit coupling, which makes which ascribes a little bit of allowedness to even spin forbidden transitions, and that is why we said in liquid state oxygen has a faint blue color. And finally, we discussed how this kind of energy level diagram, or rather this kind of arrangement of energy levels has a profound implication in the application of oxygen in biological systems, how you can have an organic molecule which you can excite to a triplet state, and this triplet state can photosensitize oxygen to produce singlet oxygen, which is very highly reactive. That can be the cause of a disease like porphyria. It can also be the basis of a treatment like photodynamic therapy. And this is what we had discussed last day. Today what we will do is we will extend our discussion to a bigger molecule, which is benzene. Benzene, of course, everybody knows the structure. What I have done here is I have shown you the character table, and since there are many symmetry operations, let us not be confused about which one is which. Okay, let us just quickly go through the character table of benzene. Of course, E everybody understands. C6 not difficult to see. Where is C6? C6 is perpendicular to the benzene ring and it goes through the center. What is C3? And why do I have two C6? Where is the other C6? Yeah. One is clockwise and the other is anti-clockwise. Great. What is C3? C3 is just C6 square, clockwise or anti-clockwise. Are we clear? Then what is C2? C2 is C6 cube, right? Start from here, C6, another C6, another C6. That is essentially a C2. Why do I not write 2C2? I have written 2C3, I have written 2C6. Why have I not written 2C2? Because it is the same, right? No matter whether you turn clockwise or anti-clockwise, you get back the same configuration. So, C2 there is only one. But then there are two more kinds of C2s, C2 dash and C2 double dash. Where are they? They are perpendicular to the C2 axis. Alright. What is C2 dash? C2 dash is a C2 axis that goes through opposite atoms, and C2 double dash is a C2 axis that goes through the center of bond. This is the convention that is followed when we write the character table. Of course, you could take the different convention, opposite convention, and write your own character table. But then the problem is your results, your molecular nomenclature and everything will be a little different from what it is in the textbook. In fact, there are textbooks in which the opposite convention is used. So, whenever we have a big molecule, we have to be absolutely sure which convention is in use there. Alright. So, we are done with all the axes. Center of inversion is very easy to understand. Then S3 is also very easy to understand, I hope. C6 axis doubles as S3 axis as well. S6 same thing. Sigma H is the plane of the molecule, horizontal plane of symmetry. Sigma D and sigma V, once again matter of convention. Sigma D is the plane that goes through the center of the bonds, and sigma V goes through the atoms. Okay. In some cases, just exactly opposite convention is followed, but the convention we have followed is this, and this is how you get this character table. And one thing that I now like to use, because otherwise the problem becomes very long, is a product table. You know what a product table is? We are working with direct products, right? So, suppose I have to do B1G cross E1G. What is it? B1G cross E1G will give you E2G. And here I have only shown a partial character table, otherwise the font size would be too small. The thing to remember is that whenever we have G cross G, we get G. Whenever we have U cross U, we get G. Whenever we have G cross U or U cross G, we get U. So, I hope it will not be difficult to use this partial character table, even if we have some U symmetries as well. Alright, great. Now, it is time to look at the molecular orbitals of benzene that we are all familiar with. These are the molecular orbitals of benzene, and I hope everybody understands what I mean when I write like this. What I have done is I have shown the p orbitals. Molecular orbitals, as you know, are generated by taking linear combinations of atomic orbitals. The atomic orbitals in question here are the pz orbitals. If you take the benzene ring to be in xy plane, right. So, you can say that whenever I have an empty circle, I am looking down from the top, right. Empty circle means say plus lobe, and solid circle means minus lobe, or the other way around, does not matter. So, when I have something like this, what would be the symmetry of that? The lowest energy atomic orbital, molecular orbital, what would be the energy? Yes, A1G. A1G is totally symmetric. Do we agree that the lowest energy molecular orbital here will be A1G? Do we all agree? I do not agree, because this molecular orbital has to be antisymmetric with respect to sigma h, right, has to be antisymmetric with respect to inversion as well. So, cannot be totally symmetric. The state will be A1G, I agree with you, because in the state we will have completely filled orbitals, but the molecular orbital is not A1G. What is the symmetry? What is the character for E? 1. What is the character for C6? C6 1. What is the character for C3? 1. So, this kind of rotation where there is no conversion from top to bottom of the plane, character should be 1. So, C6, C3, C2, all these 3 should be 1, alright. So, what is it, A or B? Has to be A, right, 1 or 2 that we will see. G or U, that we can say very easily, G or U, U. So, we do not even look at these, we look at these, okay. C2, with respect to C2, what will it be, plus or minus? C2? C2, what happens when I apply C2? This is my plane, C2 and C2 dash both are like this. If I apply C2, you see the other face, right, right. So, suppose this face is plus, this face is minus. When I apply C2, or it can be C2 dash, sorry, when it is C2 dash or C2, what am I saying? I said C2, that is why you got confused, I am sorry. C2, of course, it is plus 1, but what about C2 dash? What about C2 double dash? Character has to be minus 1. So, 1, 1, 1, 1, minus 1, minus 1, minus 1, S3, turn and reflect, minus 1, minus 1, S6, minus 1, sigma H, minus 1, sigma D, plus 1, because there is no top to bottom conversion, sigma H, plus 1. So, which one is it? You are right, it is A to U, okay. So, do not jump to conclusions because it can be tricky. A to U. These are the next higher energy pair is E1G. Of course, 2 are there degenerate, so they must belong to a 2-dimensional representation. You can work it out. The way to work it out is to actually write the expression of the wave functions. Maybe I will give it to you as a homework. So, suppose you call this psi 1 and suppose you call this psi 2, and let us say I number like this, carbon 1, 2, 3, 4, 5, 6, okay. What will psi 1 be? Minus phi 1, no sorry, what did I say? This hollow circle is plus, we said, right. So, it will psi 1 will be phi 1, where phi 1, phi 2, these are all p orbitals, pz orbitals of the atoms. Phi 1 plus phi 2 minus phi 3 minus phi 4 minus phi 5 plus phi 6. Are we clear? Of course, there will be a normalization factor, we can neglect it. What about this? Which one was 1? This is 1, right. In this case, coefficient of phi 1 is 0. So, it is phi 2 plus phi 3 minus phi 5 minus phi 6, alright. What happens when you apply C6? It will move and accordingly you can write the expression of psi 1 dash, accordingly you can write the expression of psi 2 dash. Then what you have to do is you have to generate the transformation matrix. Once you do that, you can convince yourself that this actually belongs to E1G. I will not get into that, but you can do it yourself, okay. Is there any other way of doing it? First of all, it is a 2-dimensional representation, right. If I want to take a shortcut, assuming that I have not gone wrong anywhere, I can actually work out E1G without working out the entire transformation matrix by taking some shortcut. What is the shortcut? First of all, suppose I do not know this, I know it is G, right. Can you see that it is G? This one is G. Is this also G? Of course. What about this? Is this G or U? Will these be G or U? Start from here, this is plus, go through the center, go through the other side. Remember what going through the other side means. This is plus, you have to go here, right. So, this one, is it G or is it U? These are U, these are G. So, already 1/3 of the problem is done. In fact, 2/3 of the problem is done. because you know that the only two dimensional representations are E. So, I know it has to be E, I know it has to be, I know this is U and this is G, I only have to figure out 1 or 2. So, in this case question is E1G or E2G, right. Let us see E1G and E2G, where do they differ? They differ in the character of S3 and all are very difficult to do. In the character of sigma H, right, minus with respect to sigma H, that is E1G, plus with respect to sigma H, that is your E2G, right. So, this one, is it minus with respect to sigma H or plus with respect to sigma H? Huh? Plus? No. Sigma H. So, E1G, right. So, this is my shortcut. I do not really have to work out the matrix all the time. If the character table is given, character table makes our life a lot easier, as we have actually learned in the inorganic chemistry class, where without even understanding what character table is, you could use it and get your results, right. So, here hopefully you understand a little more. Similarly, you can work out that this is E2U, and I leave it to you to work out that this is B2G, alright. I hope everybody can do this now, and I am within my rights if I ask questions on this and not necessarily in benzene, alright, great. Now let us get to the business that we really want to do. This is my electron configuration, right, in ground state and excited state, agreed. Ground state, we have, of course, we have A2U2 as well, but the HOMO is E1G4, these are fully filled. Excited state means first excited state, one electron will go from E1G to E2U. So, instead of E1G4, I have E1G3, E2U1. Understood everybody? See, if you do not understand, please ask. You are okay with the symmetries of the molecular orbitals, I hope. Now, you agree with this, that for the ground state, how many electrons are there? How many pi electrons are there? 6. How will they be filled? 2, 2, 2. So, A2U2, E1G4, okay, and all the MOs that are there are actually doubly occupied. So, what will be the state? What will be the symmetry of the state in that case, ground state? All occupied MOs are doubly occupied. In that case, Vishwarup's original answer now is correct. When all filled MOs are doubly filled, then it is a totally symmetric state, right. So, this is a singlet A1G state, okay, alright, singlet because all electrons are paired, you can just go by that. What about, what happens when there is an excitation, HOMO-LUMO excitation? HOMO is E1G, LUMO is E2U. If I have HOMO-LUMO excitation, instead of 4 electrons here, I will have 3, so I get E1G3, and now I have 1 electron in E2U, that gives me E2U1, agreed now? Okay. Now, how do I find the symmetry of this state? What are the MOs that are singly occupied? 1 E1G and 1 E2U, okay. So, to determine the symmetry of the state, I have to do E1G cross E2U. Do we agree? Because 1 E1G orbital is singly occupied, 1 E2U orbital is singly occupied. As we have discussed earlier, we get the symmetry of the overall wave function or the state by taking direct product of the symmetries of the singly occupied molecular orbitals. So, we need to do E1G cross E2U. Understood? Shambhit? Now, of course, you can do it ab initio, it is not such a big deal, but since we have this product table, we can just see what do we have to do, E1 cross E2, right. Forget GU for now, E1 cross E2, E1 cross E2, what do I get? B1 plus B2 plus E1, and in this case I am doing G cross U. So, what will be the direct product, G or U? It will be U. So, this one will be B1U plus B2U plus E1U. Please tell me if we are all okay with this. Have you all understood that since E1G and E2U orbitals are singly occupied, I have to take a direct product of those. Direct product of E1, neglecting this G and U for now, direct product of E1 and E2 is B1 plus B2 plus E1, and since I am doing G cross U, E1G cross E2U, instead of G I will have U here, right, 1 into minus 1 is minus 1. So, that direct product gives me B1U plus B2U plus E1U, alright. So, the states that you can generate are these. And see, I can have singlet as well as triplet. Now, the 2 electrons that are there in singly occupied orbitals, they are in orbitals of different energies. If the 2 electrons were in orbitals with same energy, then you would be restricted by Pauli principle, right. Not all wave functions would be allowed. But now, 1 electron is in E1G, 1 electron is in E2U. So, I can take combinations that are singlet, I can take combinations that are triplet. So, you will end up getting all these states, singlet and triplet, E1U, B2U, B1U. And the reason why we have these dashed lines and question mark is that we are working under the approximation that whatever state we generate, that is the state we work with, that is not necessary. I do not know if you have studied configuration interaction in 4 to 5. Have you studied configuration interaction in CH 4 to 5? Maybe not. That is taught in CH 560. So, when you study configuration interaction, you learn that actually states or rather electron configurations, or I can say states which have the same symmetry and same energy actually mix to produce one state with lower energy, one state with higher energy. In fact, you have encountered this situation, I am sure. Have you heard of no crossing rule? No crossing rule? Some have heard, some have not. But no crossing rule is really a manifestation of configuration interaction. But for now, let us neglect all these dashed arrows and question marks. Let us stick to singlet and triplet, E1U, B2U, B1U. If there is a question, this is the time to ask. Any question? Shubham? No question? Very good. Then we will proceed. So, yes sir. Yeah. Oh no, this what all it means is that there are 6 states. Total 6 states are there. They have shown the singlet states together and triplet states together, but actually they do not have the same energy. Do not think they have the same energy. You see, these 3 lines actually indicates that they have different energies, but which one is higher, which one is lower, we do not want to worry about that right now. That will require a rigorous quantum chemical calculation. That is all it means. What it means is that by symmetry arguments you get 3 states, singlet and triplet. Triplet is written lower because you know that everything else being same, triplet will have lower energy. But which one of these singlet states is higher in energy, which one of these triplet state is higher in energy? For that you will need to do a little more involved quantum chemical calculation. We are not getting into that. Are you okay? Any other question? Can I go ahead? Great. So now the next question to ask is, which of these transitions are allowed? See, your ground state is A1G and singlet A1G, of course, ground state is singlet, right. So, only singlet to singlet transitions will be spin allowed. Okay. We are only talking about the orbital allowedness or orbital forbiddenness at the moment. So, the implicit assumption is that we are talking about singlet to singlet transitions. Because ground state is not triplet definitely. So, singlet to triplet transitions will only occur if there is a strong spin orbit coupling. We are not talking about that at the moment. So, but from the view of symmetry only, which of these will be allowed? A1G to E1U, A1G to B1U, A1G to B2U. How do we decide which of these are orbitally allowed? How do I decide which of these are orbitally allowed? Yes? Yeah? I heard an answer. No, Laporte is different. Don't think of a general treatment. What is the transition moment integral? It is something like this, right? Psi 2, psi 1 integrated over all space, and in the middle what do you have? Mu, and mu as you know has x and y and z components. Alright. What is this psi 1? What is the symmetry? What is the symmetry of psi 1? Not just G, A1G. Psi 2 is E1U or B1U or B2U, whatever it is. Okay. So, the question is, let us say we are talking about, what is the first one we have written? E1G, E1G. So, the question is, does one of these triple products contain the totally symmetric representation? Remember, the integral is going to be non-vanishing when the integrand is totally symmetric. So, what we really have to do is to find the symmetry of the triple product and see whether it has A1G or not. Alright? Agreed? Great. So, now one good thing has happened already. Ground state is A1G, right? Ground state A1G means that multiplied by anything will give back the same thing. We do not even have to worry. We only have to worry about the direct product E1G cross whatever is the symmetry of x or y or z. Similarly, we have to worry about the direct product of B1U and whatever is the symmetry of x or y or z, B2U whatever is the symmetry of x or y or z, right. Now, one thing that you will, I am sorry. Okay, right, you are right. Have I written E1G here? E1U, you are right. Okay. So, of course, to do that I need to tell you what is the symmetry of x and y and z, and this is what is written here. I do not know if you have noticed, z is A2U and x and y together form a basis of E1U. Okay. Z is A2U and x and y together is E1U. Alright, that comes from the character table. Now, with this information, without doing anything else, without looking at the character table or without looking at the product table, can you tell me whether this A1G to E1U transition is allowed or not? Allowed? Why, Raksha? So, Raksha is trying to do it by Gerade and Ungerade only, but do not forget that Gerade and Ungerade only tell you about inversion. So, it can tell you whether something is not allowed, but there might be transitions that seem to be allowed because it is Gerade Ungerade, but it might not be allowed by something else. You have to look at all symmetry operations. And if you remember, one small working formula that we have worked out is, you have this gamma I cross gamma j. When will it contain, say, A1G? We had worked this out. When will the direct product gamma I cross gamma j contain a totally symmetric representation? Yes? When both are same, of course they will contain. Remember that? Then every 1 will be multiplied by a 1, every minus 1 will be multiplied by minus 1. So, when both are same, definitely they will contain totally symmetric representation. So, you see E1U and x and y together form a basis of E1U. So, E1U cross E1U must contain A1G. So, it is allowed, okay, or vitally allowed. And then if you want to do a little more detailed treatment, we can see. So, this is what we are trying to evaluate, right. First one is A1G, you do not worry about. Here the problem is it is written in the other way compared to what we are working, but does not matter. E1U cross A2U or E1U, B1U cross A2U or E1U, B2U cross A2U or E1U. So, even without working out anything more, you can I think see that A1G to E1U is allowed, and it is allowed through x and y directions. The other two are not allowed orbitally, alright. And then to convince us a little further, let us take help of this product table and let us see what the direct products are. A2U cross E1U, A2 cross E1, what is it? E1, E1G, because you are doing U cross U. E1U cross E1U, what is it? E1, E1 will give me A1 plus A2 plus E2. Should it be G or U? I am doing E1U cross E1U, G, right. So, it will be A1G, and this is our A1G, this is what we are looking for. A1G plus A2G plus E2G, this is what you will get, right, and this A1G is what makes it allowed. What about A2U cross B1U? A2 cross B1, what do you get? B2, and should it be G or should it be U? Yeah, A2U cross B1U, G, B2G, and E1U cross B1U is also E2G. Similarly, you can work out these as well, and you can convince yourselves that in only one case I get A1G, and that is A1G to E1U transition. So, that is what tells us that singlet A1G to singlet E1U is a fully allowed transition. What is the meaning of fully allowed transition? Spin allowed as well as orbitally allowed. The other two are orbitally forbidden, alright. So, this is what we arrive at, that for benzene, now we know what the symmetries of the orbitals are, we know what are the ground state and excited states involved, at least for the lowest energy transitions, and we have been able to determine which of these transitions are fully allowed, which of these transitions is fully allowed and which are not orbitally allowed. Of course, singlet A1G to singlet B1U, is it spin allowed? This transition here, of course, it is orbitally forbidden. Is it spin allowed? Forget the orbital part, singlet to singlet, that is spin allowed, right? Singlet A1G to singlet B2U, orbitally forbidden, I agree. Is it spin allowed? Right? Yes, it is spin allowed. Suspender has a doubt. Doubt? Fine. You agree with me that for these two transitions, they are orbitally forbidden? Now, I am asking you to forget about the orbital part for the moment. I am saying both of these are singlet to singlet transitions. So, from the point of view of spin, are they allowed or are they not allowed? Remember what the transition moment integral is, or how we wrote it. We wrote transition moment integral as psi s dash psi s integrated over all space psi v dash psi v integrated over all space psi e dash mu psi e integrated over all space. So far what we have discussed is this, right. This part we have said that for until now in our discussion we said that this is the Frank-Condon factor, it decides the intensity. This part decides whether a transition is spin allowed or not, alright. So, if I forget about the rest of the factors, think only about this, then I know that singlet to singlet is a spin allowed transition, that is what I am saying, that even though it is orbitally forbidden, it is spin allowed. Does not mean that we are going to see a band corresponding to it, we will see what happens, right, but it is a spin allowed orbitally forbidden transition, agreed. and the first one is a fully allowed transition. Okay. So, in the next part we will see whether there is any way in which this orbitally forbidden transitions can become allowed or not.